In light of the universe's immense size, scientists have recently proposed the idea that it is expanding. However, this expansion is not happening as a result of galaxies traveling through space, but rather as a result of the fabric of space between them stretching. So if the universe is indeed expanding, what is it expanding into? Is there anything beyond space itself, or is it just the universe itself stretching? In the beginning of the 20th century, scientists generally believed in a static, unchanging universe. That is, a universe that had always existed with galaxies and stars fixed in place. However, this view began to change as astronomers looked more closely at faraway galaxies. An influential figure in this change was the American astronomer Edwin Hubble, whose observations would fundamentally alter our understanding of the cosmos. At the time, the most powerful telescope in the world, the recently assembled 25M Large Hooker Telescope, was available to Edwin Hubble at California's Mount Wilson Observatory. With this instrument, Hubble studied far-away, faint objects in the night sky. At first, it wasn't clear if these objects were part of or separate from our Milky Way galaxy. However, Hubble eventually proved that many of these specks of light were, in fact, whole galaxies located far beyond our own. In the Milky Way, as Hubble persisted in his studies, he made an astonishing discovery. Light from faraway galaxies is shifted toward the red end of the spectrum. This is called red shift, and it happens when light waves are stretched out, making them appear redder. It's like the Doppler effect, except instead of sound, it's light being stretched. Red shift suggests that. It appeared that all the galaxies that Hubble studied were receding from one another, which led him to the revolutionary conclusion that the universe wasn't static but rather expanding, as observed by the fact that the red shift, or speed of a galaxy's motion away from Earth, increased as its distance from the Sun increased. This finding, which Hubble later came to be known as Hubble's law, was confirmed by his extensive observations of galaxies. Hubble's discovery revolutionized astronomy and our understanding of the universe. It revealed that the universe was not as eternal and unchanging as previously believed, suggesting that in the past, they were closer together. This led to the theory that the universe had a beginning, when everything was condensed into a small, extremely dense state before expanding outward. This theory laid the foundation for what would later be called the Big Bang Theory. Rather than that, it was dynam DC with galaxies continually receding from one another. This led to a different way of looking at the universe, which held that it had started at some point and has been growing ever since. When we talk about the universe expanding, we're not simply talking about galaxies moving apart in space. It's more like the space between them is actually stretching. This is a very important point. Distinction because it alters our conception of the structure and growth of the cosmos. When we speak of the universe's expansion, we mean that space itself is growing in size. To better understand this, it's helpful to picture the cosmos as a balloon, with galaxies as tiny dots on its surface. As the balloon expands, the surface stretches, and the dots move farther apart, not because they're moving across the surface, but because the surface is expanding. This is analogous to what? Phenomena in the cosmos. The idea of space expansion alters our conception of the cosmos. Typically, we picture space as a stage upon which celestial bodies, such as planets, stars, and galaxies exist and travel. However, in an expanding universe, space is inherently dynamic and constantly stretching, making galaxies appear to recede from us at an ever-increasing rate. Astonishing rates of expansion. One peculiar outcome of this theory is that there are galaxies so distant from Earth that we will never get a glimpse of them. The distance between us and these galaxies is growing at such a rate that the light they produce can't reach us. It's as if space itself is transporting them out of our field of vision. What this means is that despite the vastness and abundance of the universe, there are portions of it that we will never be able to study or observe. These regions are located beyond the observable universe, the part of the cosmos from which light has been able to reach Earth since the Big Bang. Fascinatingly, the expansion of the cosmos does not impact nearby galaxies or other objects such as our solar system and the Sun, which means that objects such as these are being held together by gravity rather than being pulled apart by the expanding space between them. Space is expanding at all points in the universe, so there is no one spot where expansion is occurring. Instead, it appears as though galaxies are moving away from any particular galaxy when viewed from within that galaxy. This was a challenging concept for scientists to grasp at first, since it calls into question long-held assumptions about the nature of space and the nature of space itself. The story of cosmic expansion doesn't start with a steady stretching of space. Rather, it begins immediately after the Big Bang, when the universe experienced a brief but incredibly intense period of expansion known as inflation. Although it happened in a fraction of a second, it had a loss impact on the universe as we see it. What we perceive as movement in our everyday lives is actually the background changing in the universe, thanks to cosmic inflation and dark energy. Right after the Big Bang, the universe was a dense, hot soup of particles and energy. However, space started to expand at a rate far faster than it is now during an inflationary period. In that brief instant, the universe went from being smaller than an atom to being larger than a light year. This rapid expansion did two things. It made the universe remarkably uniform by smoothing out any irreversible singularities, and it caused tiny fluctuations in density. Inflation spread everything out, making the universe large and mostly homogeneous with slight variations that allowed for the formation of galaxies and other structures. This brief period set the stage for the slower expansion that followed, leading to the universe's current size and shape. Fluctuations would later become the seeds for galaxies and stars. Without inflation, the universe as we know it might never have formed in a way that could support life. Observation of distant supernovae, which are enormous explosions that happen when specific kinds of stars die out, in the late 1990s led two groups of astronomers to the surprising conclusion that the expansion of the universe is actually speeding up rather than slowing down, as was previously believed. This discovery came as a shock to scientists who had anticipated that the expansion would slow down over time as a result of the gravitational pull of galaxies and other matter. By observing these supernovae, astronomers were able to gauge the rate of expansion of a universe from Precambrian times to the present. To their astonishment, they discovered that distant supernovae were less bright than anticipated, indicating that the galaxies they belonged to were distant from Earth. This, in turn, meant that the expansion of the universe was being accelerated rather than slowed down. The mysterious force responsible for this acceleration has been dubbed dark energy, and its nature continues to baffle scientists. Comprises approximately 70% of the total energy in the universe, but its exact nature remains a mystery. What is known is that it appears to be a force that opposes gravity, driving galaxies apart at an exponentially increasing rate. Unlike ordinary matter or dark matter, dark energy does not appear to condense, but rather to be uniformly distributed across space, impacting the universe on a massive scale. Deciphering dark energy is a major undertaking in the field of cosmology, as it is instrumental in, has long confounded scientists and physicists. One theory proposes that dark energy is intrinsic to space itself. As the universe expands, more space is created, and so is dark energy. This would indicate that the expansion of the universe feeds into itself, with dark energy becoming stronger with each passing second. Another theory places dark energy in relation to the cosmological constant, a notion first proposed by Albert Einstein in his general relativity equations. Einstein first included the cosmological constant to hold the universe still, as the concept of an expanding universe hadn't been discovered yet. However, after Hubble's observations proved that the universe was actually expanding, Einstein discarded the cosmological constant, claiming it was his greatest mistake. However, with the discovery of dark energy, the idea has been revived, and some scientists now believe that the cosmological constant could indicate the existence of dark energy, an inherent component of space-time. Begs the question, what will happen to the universe when its expansion rates continue to skyrocket? Will galaxies eventually freeze up, starlight dwindling, and the cosmos turning into a frigid, dark wasteland? Or will the expansion rates skyrocket to such extremes that even atoms and galaxies are ripped apart? While these theories are still in the realm of speculation, they do show how dark energy could significantly alter the course of the cosmos's evolution in the far future. The expansion of the cosmos has not been a static process spanning billions of years. Rather, it has changed throughout its history, most notably in the early moments following the Big Bang and the inflationary period when the cosmos expanded at an unprecedented rate. Astronomers measure a value known as the Hubble constant to understand the rate of the universe's expansion. The constant tells us how fast galaxies are moving away from each other depending on their distance from each other, and it represents the delicate balance between the initial outward force from the Big Bang and the inward pull of gravity. Throughout the universe's evolution, this constant has played a significant role. An important cosmological constant, the Hubble constant, measures the rate of galactic expansion with respect to distance from Earth in kilometers per second per megaparsec. A megaparsec is a unit of distance used by astronomers that is equivalent to approximately 326 million light-years. Using the Hubble constant, we can calculate the rate of galactic expansion for a galaxy that is 1 MEAP park away in kilometers per second. The distance to distant galaxies and their velocities can be determined through the use of a specific type of star known as a Keyed variable. Keyed variables are stars that undergo periodic brightness increases and decreases. What makes them useful for this purpose is that their pulsation period is proportional to their actual brightness, which can be determined by comparing the star's actual brightness to. In order to determine the Hubble constant, astronomers need to know both the distance to a galaxy and the speed at which it is moving. By observing the red shift of a galaxy's light, which occurs when its light is stretched to longer, redder wavelengths as it moves away from Earth, we can gauge the galaxy's motion and how bright it appears to us on Earth. There are two main ways to determine the Hubble constant, and they aren't entirely in agreement with each other. One way uses objects like Cepheid variables and supernovae as distance measurements, while the other uses the distances to galaxies and their red shifts. Different teams of astronomers have come up with slightly different measurements over the years, leading to the so-called Hubble tension, a scientific debate about the exact value of the Hubble constant. Marker method, which is based on nearby galaxies and gives a Hubble constant of around 73 kilometers per second per megapark, and another method that uses data from the early universe, specifically the cosmic microwave background, CMB, which is a snapshot of the universe at its youngest point, about 380,000 years old, and allows scientists to calculate the speed of expansion shortly after the Big Bang by analyzing patterns in the CMB. The Hubble constant has been estimated using models of cosmic evolution and the Big Bang theory. However, measurements from the cosmic microwave background, CMB, indicate a slightly lower value for the Hubble constant, around 67 kilometers per second per megapark. This disparity, though seemingly small, is significant enough to raise questions about whether our current understanding of the expansion of the universe is complete, as both methods should yield the same result. Moreover, the fact that they don't suggest that something could be absent from the present universe models. Another possibility is that there is some undiscovered physical principle at work here. Our current universe models are based on assumptions about things like dark energy, dark matter, and gravity's behavior. If even a small deviation from these assumptions explains the discrepancy in the measurements, for instance, if dark energy doesn't behave exactly as we expect, it could impact the expansion rate in ways we haven't yet discovered. Einstein's theory of general relativity suggests that there may be changes in the way gravity operates over very long distances, which could explain why our current understanding of the expansion of the universe differs from that of its early days. Another possibility is that the universe contains exotic matter or energy that has not been detected yet. If this is the case, it could have affected the rate of expansion in the past, which would explain why our current understanding of the universe differs from that of the early universe. We have never directly tested how gravity behaves on the largest scales of the universe. If gravity works a little differently across cosmic distances, it could influence the expansion rate in ways we don't fully understand. Some scientists have proposed modifications to general relativity to account for this, which would make things more complicated. However, general relativity has been remarkably successful in describing the behavior of gravity on smaller scales, like within our solar system or even galaxies. Space distance measurements are notoriously difficult, so it's reasonable to wonder if the discrepancy is due to small mistakes in our observations or calculations. For instance, some researchers have questioned whether we have a complete grasp on the characteristics of seed variables or supernovae. A mistake in calculating their actual brightness, for example, could skew our distance measurements and, in turn, our. The analysis of the cosmic microwave background, CMB, relies on intricate models of the early universe's evolution. If these models are flawed, it could impact the predicted value of the Hubble constant. Therefore, researchers are going back over the assumptions made by these models to see if anything was overlooked or misunderstood. As the universe has expanded, the rate of expansion has changed, and gravity had a major impact on. Around 98 billion years ago, the expansion rate slowed down due to the expansion of the universe. At around 4 billion years ago, the expansion rate started speeding up again, driven by dark energy. With the advent of new technologies, astronomers hope to get closer to the truth, so they are searching for an accurate measurement of the Hubble Space Telescope. One of the basic forces of nature, expansion of the universe, raises questions about how this force interacts with the stretching of space on both large and small scales. On the large scale, galaxies are moving apart as space itself grows, and new telescopes and observatories like the James Webb Space Telescope are helping astronomers refine their measurements and get closer to a definitive value for expansion and the limits of gravity. Einstein's theory of general relativity describes gravity as the force that pulls objects together. It is responsible for the formation of galaxies, the clustering of galaxies into larger structures, and the orbits of planets around stars. Without gravity, the universe would be far more chaotic, with matter spread out randomly rather than organized into these seemingly contradictory clusters. Galaxies, stars, and clusters of galaxies are all affected by the same thing: gravity. Objects with more mass are pulled closer together by the fabric of space-time, and a stronger an object's gravitational pull, the more the universe is expanding. Unlike cars moving through space, galaxies are actually pulled farther apart by the stretching of space itself. This expansion is happening on the largest scales, affecting clusters of galaxies and galaxies that are millions or even billions of light years in diameter. At large distances from one another, the expansion of the universe appears to have little impact on larger systems like galaxies. This is because the pull of gravity is significantly stronger at smaller scales compared to the effects of cosmic expansion within a galaxy. For instance, the mass of stars, planets, and dark matter forms a strong gravitational field that holds everything bound together. Therefore, at these smaller scales, the expansion of space is so weak that it is effectively canceled out by the pull of. Because of the force of gravity, neither galaxies nor stars can be seen to be expanding or drifting apart. Such phenomena can only be observed at extreme distances, measured in millions or billions of light years. For instance, the Milky Way and its neighboring galaxy Andromeda are not expanding apart as a result of cosmic expansion, but rather are being pulled together by their mutual gravitational attraction. Galaxies within a cluster are held together by gravity, even though the space between them is expanding. This is why the expansion of the universe is often said to occur on a cosmic scale, the largest scale that we can observe. Galaxy clusters are among the biggest structures in the universe, and even though the space between them is expanding, the galaxies within a cluster are bound by gravity. Galaxy clusters are held together by gravity within the clusters themselves. But as the universe expands at an accelerating rate, driven by dark energy, will gravity eventually lose its hold on galaxies and galaxy clusters as a whole? Some scientists believe that if dark energy becomes powerful enough, it could eventually overpower gravity, causing galaxies, stars, and even atoms to disintegrate. In a future scenario called the Big Rip, space would expand to the point where nothing could remain connected, leading to the end of the universe as we know it. However, for the time being, gravity holds things together. Scientists are still trying to figure out one more thing about the interaction between expansion and gravity, and it involves dark matter. Dark matter is an invisible type of matter that doesn't interact with everything else. Light, but it comprises the bulk of the mass in galaxy clusters and galaxies themselves. The gravitational pull of dark matter keeps galaxies bound together even when the mass of their visible components, such as gas and stars, doesn't appear to be sufficient to keep them from collapsing. Without dark matter, galaxies would be more vulnerable to cosmic expansion because their mass wouldn't be strong enough to generate strong gravitational fields. As we gaze into the infinite space, light from faraway galaxies takes millions, if not billions, of years to reach Earth. This light becomes increasingly older as we move further away from the source, thanks to the universe's constant expansion. However, there's a limit to how far we can see, a boundary called the cosmological horizon, which is an essential part of the delicate equilibrium between gravity and the expanding universe. Although light travels at the speed of light, the expansion of space itself can carry galaxies with it. As a result, light from galaxies beyond a certain distance is stretched out and redshifted until it disappears from view. Beyond this point, light from distant objects hasn't had enough time to reach Earth, and these regions remain beyond our observational reach. This limit is known as the cosmological horizon, sometimes called the observable universe. It doesn't mean the universe ends beyond this point. Rather, it marks the limit of what we can see with our eyes. Beyond this horizon, there may be innumerable galaxies, stars, and other structures, but we can't see them because light from those faraway places hasn't had time to travel to our vantage point. The observable universe is a tiny fraction of the universe as a whole, and we might never be able to see beyond this horizon, no matter how long we wait. As time goes on and the universe continues to expand, more and more distant regions send light our way, increasing the size of what we call the observable universe. However, due to the rapidity with which the universe is expanding, some of these regions may one day disappear beyond the cosmological horizon, rendering the galaxies we see today invisible as their light becomes redshifted and stretched out beyond detection. The rate of expansion of space is increasing, which means that the number of galaxies visible to the naked eye may be decreasing as they pass beyond our field of view. All our knowledge of the cosmos is based on observations made within our observable horizon, and since the universe is much bigger than that, there's a great deal of information, including galaxies and cosmic structures, beyond that frontier that we are unable to access, and maybe even other parts of the cosmos that are too distant for us to ever observe. Several important factors define the cosmic horizon, the most important of which is the age of the universe. At its current age, the universe is approximately 138 billion years old. Since light can only travel to us at a finite speed, the furthest objects that we can see are around 138 billion years old. However, this distance has been increasing due to the expansion of the universe. Although light from faraway galaxies traveled toward Earth, the distance between us and those objects grew, increasing the distance between us and those objects, even though the light took 138 billion light-years to reach us. In fact, the present distance to the edge of the observable universe is estimated to be approximately 46 billion light-years. This may appear contradictory, but it makes sense when we think about the expansion of space. While the cosmological horizon does mark the limit of what we can observe, it does not indicate the end of the universe. The universe likely continues beyond this horizon, but we will never be able to directly see or interact with it. The question of what lies beyond the observable universe has fascinated scientists for decades, leading to numerous theories and speculations. Now, the distance to those galaxies is significantly larger due to the expansion of the universe. When considering the vastness and impossibility of accessing space, one basic idea is that beyond our horizon, the universe appears much as it does from Earth. This is based on the principle of cosmological homogeneity, which states that, on a large scale, the universe is uniform and appears the same in all directions. If we could somehow peer beyond our observable universe, we could potentially find more galaxies, stars, and cosmic structures that resemble what we see in our own. Beyond the horizon, there might be variations in the density of matter and energy. Some regions could contain more galaxies and matter, while others might be less dense. These variations would be invisible to us, but they could happen. This would mean that the observable universe is just a small part of a much larger universe that extends far beyond what we can see. Going beyond the observable universe is the idea of a multiverse. Some cosmological interpretations, especially those based on inflationary theory, propose that our universe may actually be one of numerous pocket universes or bubbles that formed during the early stages of cosmic inflation. In this scenario, the fast expansion of the universe could have far-reaching consequences for our overall understanding of the cosmos. The expansion of space during inflation created separate regions of space-time, each with its own unique properties. Our observable universe is just one of these regions. There may be other, inaccessible regions beyond the horizon that are even more different from our own. These regions may have different physical laws, constants, or even a number of dimensions. The concept of a multiverse implies that the inaccessible regions beyond the horizon may contain entire universes with their own extraordinary structures where the basic laws of physics act in ways that are totally foreign to us. Although this is just a theory and not something we can test, it does provide an intriguing glimpse into what might be out there beyond the visible cosmos. Even if we take it as a given that the OB is comparable to our own, the expansion of the cosmos still has a significant impact on these faraway places. As space expands, the OB is receding from us. The vast expanse of space between galaxies is increasing with the passage of time. As the universe expands, the distance between galaxies in these faraway regions will also grow, just as it does in our visible universe. This implies that cosmic expansion is shaping the evolution of the universe even beyond our view. Looking ahead, regions beyond the horizon may become even more isolated from our visible universe if the expansion pace keeps increasing. It's conceivable that, as a result of dark energy, more and more areas of space will gradually recede from the visible light spectrum, effectively cutting off portions of the universe from one another. In this scenario, the cosmos could fragment into smaller and smaller pieces, with vast stretches of empty space separating isolated pockets of galaxies. These regions would still exist, but they wouldn't be able to communicate with or learn from each other. Space is becoming increasingly isolated as it expands, gradually pushing everything beyond the cosmological horizon. This means that we can only speculate about what might be in those distant regions, as we will never be able to directly observe or confirm these ideas. When you consider the nature of space, you start to wonder if it is infinite or expanding into something. The question of whether space is expanding into something bigger or if it is infinite in and of itself is fundamental to the nature of both space and time. If space is expanding, does it have a limit or does it stretch on forever? If space is expanding, is it into a larger framework or is the idea of expansion more abstract? If space is infinite, then there is no edge or boundary. It just is, stretches endlessly in every direction. In this scenario, the expansion of the universe means that, despite space's infiniteness, the distances between objects in that space are increasing no matter how far you travel. The idea of an infinite universe without any outer edge to speak of is hard for us to understand because we're used to thinking about things with limits and boundaries. On the other hand, some theories propose that the universe might be finite but unbounded, which would mean the universe may be finite in size, but without a boundary or edge where space simply stops. This is similar to how a balloon works. There's a finite amount of space on the surface, but if you travel in one direction for a long enough time, you could end up back where you started, just like traveling around the Earth. Another possibility is that the universe may be infinitesimally small. The universe is expanding into something, but what exactly is it expanding into? In our everyday lives, when we think about things growing, we usually picture them taking up more room. However, when we consider the universe as a whole, we see that space is expanding, not into anything specific but into itself. This is because space and time are intrinsic to the cosmos, so any concept beyond it remains a mystery. If our universe is just one of many coexisting universes in a vast multiverse, then the space around us may also be part of a grand design. Nevertheless, the expansion we see need not be our universe growing into this grand multiverse. Rather, it is the stretching of space itself. As for what lies beyond our universe, that is still up for debate. On the tiniest scales, quantum theory suggests that space's fabric is far from smooth. On the most microscopic scales, space is believed to be a chaotic, constantly shifting terrain called quantum foam. This foam stands for the energy fluctuations that happen at extremely microscopic scales, where the laws of quantum mechanics take center stage. Particles in this quantum realm can appear and disappear in the blink of an eye, and space itself can act erratically. The question of whether the universe is infinite at larger scales but fundamentally granular or discrete at smaller ones has long perplexed scientists. If this is the case, then the idea of infinite space becomes even more complicated. Meanwhile, quantum mechanics operates at minuscule scales, and some have speculated that there may be a link between the two. Could quantum fluctuations at the smallest scales affect the expansion of space itself? This is still a highly active area of research. Research as scientists endeavor to bridge the apparently disparate realms of quantum mechanics and cosmic expansion. Curved space could potentially alter the universe's shape due to expansion. In terms of the structure of the cosmos, curvature is crucial, and the shape of the cosmos is intimately related to its expansion. For a long time, scientists have argued over whether the universe is flat, closed, or open, and there are three possible scenarios regarding the curvature of space. While it's difficult to visualize, this curvature has a direct impact on how the universe evolves. The expanding universe exhibits certain behavior at the largest scales. The idea of curved space originates from Einstein's theory of general relativity. According to this theory, massive objects, such as galaxies and stars, distort the space around them, causing the force we perceive as gravity. While this curvature is typically quite small at smaller scales, such as within our solar system, it can take on one of three forms at larger scales: flat, closed, or open. The curvature of the universe is determined by the total mass of all possible subatomic particles in the universe. The quantity of mass and energy contained within the universe determines its shape. A flat universe means that space extends in all directions without bending back on itself. In this model, parallel lines would stay parallel indefinitely, and the sum of a triangle's angles would always be 180 degrees, similar to how they appear on a flat sheet of paper. A closed universe, on the other hand, would have space curving in on itself, while an open universe would have space expanding irrepressibly. Similar to the surface of a sphere, in this scenario, if one were to travel in a single direction far enough, they would eventually return to their starting point. In a closed universe, the total mass and energy would be so great that the expansion of the universe would come to a halt and contraction would set in. When all matter and energy are pulled back together by gravity, the universe would collapse. In contrast, an open universe would. In an infinite universe with negative curvature, like a saddle, space would expand indefinitely, with galaxies moving farther and farther apart at an exponential rate. There wouldn't be enough mass or energy for the universe to ever condense itself, so expansion would continue indefinitely. In such a universe, the sum of a triangle's angles would be less than 180 degrees, and parallel lines would eventually diverge, meaning that expansion would slow down with time. As the cosmos expands, its mass experiences a gravitational pull. If the universe were closed, expansion would halt and reverse, causing the Big Crunch. On the other hand, if the universe were open, expansion would continue forever, albeit at an ever-increasingly slow pace. One of cosmology's primary objectives is to ascertain the universe's shape. By analyzing the cosmic microwave background, CMB, scientists have measured the curvature of space on large scales, and these measurements indicate that the universe is remarkably flat. The universe does not exhibit a discernible curvature on cosmic scales. This does not imply that the universe is perfectly flat, but rather that any such curvature is so minute that it cannot be detected using our present-day instruments. Nevertheless, just because the universe is flat does not guarantee that it will continue to expand at a constant rate indefinitely. Our understanding of cosmic evolution has been transformed by the discovery of dark energy, which is driving the expansion of the universe at an unprecedented rate, regardless of the curvature of the universe. There's a theory that explains how the universe became so flat: cosmic inflation. This theory proposes that the total density of mass and energy in the universe is very close to a critical value, and any small deviation from this balance would have caused the universe to be either closed or open. If the universe is flat, as current evidence suggests, then space itself continues to stretch and galaxies move apart at increasing speeds. Small scales, such as within galaxies or clusters of galaxies, the curvature of space due to gravity is very much a reality. The gravitational pull of massive objects warps the space around them, bending light and affecting the cosmos. Despite the flatness of a universe on large scales, the effects of inflation may still be present in ways we don't fully understand. The local curvature of the space around stars and planets doesn't affect the expansion of the universe on a grand scale, unlike large-scale curvature. It's conceivable that there's a tiny curvature of the universe that we haven't noticed yet. If it's slightly closed or open, the effects would be so tiny that they wouldn't be noticeable unless we traveled great distances, which is far beyond our current observable range. Perhaps when technology and measurements advance, we will have a better idea of the universes. The curvature of space and its interactions with the ongoing expansion of space determine the fate of distant galaxies and their destinations within the expanding universe. As a result, galaxies far from Earth are receding at an accelerating rate, which will eventually surpass the speed of light. Although this may seem counterintuitive, it is crucial to consider the implications of this phenomenon. Keep in mind that this isn't breaking any physical laws. Rather, it's space expanding to accommodate these galaxies, not the galaxies themselves. This difference is critical for comprehending what will happen to these faraway galaxies and how the universe will evolve in the future. As space expands, these galaxies will gradually recede from our line of sight until their light can't be. Galaxies will eventually fade from view as the expansion of space surpasses the capacity of light to traverse it. This is a gradual and ongoing process. At present, some galaxies are so distant that their light barely reaches us. As time goes on, these galaxies will move farther apart, and eventually we will be the only ones left to observe the universe as it shrinks. As galaxies recede from Earth, the light they emit is stretched into longer wavelengths, moving toward the red end of the spectrum. The faster a galaxy recedes, the more its light is redshifted, and eventually it will be redshifted beyond the visible spectrum, making it invisible to even the most sensitive telescopes. This phenomenon is known as the redshift effect. Telescopes in the distant future, billions of years from now, the vast majority of galaxies will have dwindled in size until they are no longer visible to the naked eye. In that point in time, the only galaxies that will still be within our local group, including the Andromeda Galaxy, the Milky Way, and a handful of smaller neighboring galaxies, will still be visible to us, close to one another, and will eventually combine into one large galaxy. However, outside of this local cluster, the rest of the cosmos will be invisible to us as faraway galaxies fade into the darkness at the speed of light. This future scenario suggests that we are becoming increasingly alone in the universe, as each galaxy crosses the cosmic horizon, taking with it the stars and galaxies that were once visible to us. Astronomers of the future may mistakenly assume that the Milky Way or the merging galaxy it becomes constitutes the entire universe due to a lack of information about its past, leaving us in an increasingly dim and lonely cosmos. As galaxies recede from each other, the likelihood of interaction between them decreases, and observers within our galaxy may never know that there was ever a vast universe filled with innumerable galaxies. During the early universe, galaxies frequently merged and collided, creating larger structures and causing star formation bursts. However, as time passes, the universe will grow quieter and more isolated, with fewer opportunities for galaxies to influence each other. In the far future, after distant galaxies have disappeared beyond the cosmic horizon, the universe will be very different. The stars in our galaxy will still be burning brightly for billions of years, but in due time, even they will fade away, and the universe will become colder and darker as stars die out and new ones aren't born. This period is called the heat death of the universe. It occurs when the universe has expanded to the point where it can't support the dynamic processes that shaped its early evolution. Some wonder if this acceleration of cosmic expansion could change the laws of physics. This question challenges the assumption that throughout the universe's history, fundamental constants like the speed of light, the strength of gravity, and the fine structure constant have remained unchanged. This stable framework has been provided by most models of physics, but as the universe expands and evolves, some theorists have questioned whether this process could gradually alter or impact the laws that govern reality. To grasp this idea, one must first recognize the fine structure constant governs the interaction between light and charged particles, playing a critical role in chemistry and the formation of matter. The speed of light, for example, determines how fast information can travel across space. The gravitational constant, on the other hand, dictates how strongly objects with mass attract one another, and these values constitute the backbone of physics as we know it. A slight variation in even one of these constants could result in a universe that looks drastically different from. It is worth considering the possibility that the constants governing these interactions may undergo slight changes as space stretches, as the universe expands, especially due to dark energy. This stretching impacts the growth of distances between objects and the evolution of the universe on large scales. Some have even speculated that the constants we observe now may not have been the same in the distant past. One area where this idea is getting some attention is in the context of the fine structure constant, which governs the expansion and contraction of the universe. For example, there's a chance that the early universe's electromagnetic and gravitational forces were different, which could have altered the circumstances for the formation of stars, galaxies, and other cosmic structures. Scientists continue to debate whether the fine structure constant was slightly different billions of years ago. If this variation were confirmed, it would indicate that cosmic expansion or other cosmic processes could subtly affect the constants of nature, such as the strength of the electromagnetic force, if dark energy behaves in ways we don't fully understand. The expansion of the universe may impact our perception of time as the distances between objects grow and the wavelengths of light lengthen. However, could this same stretching of space impact the fundamental flow of time? Other, more far-fetched theories propose a connection between dark energy and cosmic evolution that could alter the constants of nature. Some theories propose that as the universe cools and expands, the laws governing high-energy processes might shift into new states, causing fundamental forces to change in ways that are currently unimaginable. This could potentially lead to phase transitions in the universe, where the laws of physics reorganize themselves under new conditions, drastically altering the nature of the constants of nature and perhaps spawning new forms of physics altogether. Similar to how water turns into ice at specific temperatures, our current universe could undergo a drastic change in the next billions or trillions of years due to the effects of expansion on cosmic structures. These structures, such as galaxy clusters, filaments, and voids, are the product of gravity drawing matter together over long periods of time, creating vast networks of interconnected galaxies. The expansion of space is pulling galaxies apart, creating a cosmic tug-of-war between attraction and separation. As a result, the fabric of the universe is stretching and taking on new shapes on the largest scales. At its core, the universe is organized into a web-like structure called the cosmic web, which is made up of long filaments of galaxies that link denser regions called. As the universe expands, the space between galaxy clusters and filaments swells, creating vast empty spaces called voids where few galaxies can be found. As a result, the galaxies within clusters are held together by gravity. But as the space between filaments stretches, the voids grow and the galaxies within them are squeezed apart, a phenomenon known as cosmic drift. The ever-increasing distance between galaxies is causing a decline in the frequency of interactions like galaxy mergers, which were common in the early universe. As a result, the cosmic landscape is becoming less active, making it harder for galaxies to collide, exchange matter, or influence each other through gravitational interactions. One notable impact of cosmic expansion on cosmic structures is the growth of voids, which are large empty regions between galaxy clusters. The universe is expanding, which is driving galaxies farther apart and creating a more fragmented large-scale structure. In the far future, these voids will dominate the visible universe, and galaxy clusters will look like isolated islands within the expansion. The gravity within galaxy clusters is strong enough to counteract the expansion of the universe, so the galaxies in them stay bound to each other. And even though space is expanding, they don't drift apart as much as. Galaxy clusters in less dense regions of space are still linked by filaments of galaxies, but these connections are weakening as the universe expands. Eventually, the filaments will be stretched to the point where they can no longer hold together, causing the galaxies within the clusters to drift apart. For the time being, the clusters will remain intact due to their own gravitational pull, but the distances between them will increase exponentially. In the future, as the distances between clusters increase, these groups of galaxies will grow farther apart, creating a vast expanse of empty space. As the universe expands, fewer galaxies will be visible from any particular location because the light from faraway galaxies will be warped and redshifted until it becomes undetectable. As a result, the observable universe will contract, not in absolute terms, but in terms of the number of galaxies that observers in any particular galaxy may be able to make out. Clusters of galaxies, while the rest of the cosmos fades away beyond the cosmic horizon. The processes that have molded galaxies, like star formation, gas and dust exchange, and mergers, will inevitably slow down as the universe ages. In the early universe, galaxies were formed when gas and dark matter collapsed into small spaces. However, as the universe expands, the density of matter decreases, making it harder for new galaxies to form. Existing galaxies will keep evolving, but as time goes on, the process of new galaxies forming from primordial gas clouds will become less common. Eventually, the universe will reach a stage where no new galaxies are being formed, and the existing ones will continue to drift apart. The gaps between cosmic structures will grow so large that not even light from faraway galaxies can bridge the distances, leaving us with an expanding universe that is silent and dark. The relationship between time, space, and the expansion of the universe suggests that time may not be as static as it appears. According to general relativity, space and time form one entity called spacetime. Therefore, any change to space, such as its curvature around massive objects like stars or its stretching as the universe expands, can impact the flow of time. Time is affected by the expansion of the universe, which causes the distances between objects to grow and the fabric of space-time to stretch. However, does this stretching affect how we perceive the passage of time? In our local environment, we don't perceive the effects of cosmic expansion because our clocks continue to tick at a steady pace. The Earth continues to orbit the Sun, and the Sun rises and sets at regular intervals. This is due to the fact that on smaller scales, such as the ones we encounter on a daily basis, the influence of gravity is paramount in maintaining the dimensionality of objects like galaxies, planets, and stars. On larger scales, such as those we encounter in space, the relationship between time and expansion becomes more intricate. As space expands, the light that travels through it also stretches, resulting in the red shift that we see in faraway galaxies. This red shift not only stretches the light waves, but it also impacts our perception of time from faraway objects. When light from distant galaxies arrives at Earth, it does so at a slower rate than when it is closer to the galaxy. This effect, known as time dilation, is a direct consequence of the universe's expansion and means that events unfolding in distant galaxies appear to take longer than they actually do. Time seems to be moving more slowly when we look at faraway galaxies or supernovae than it is when we're on Earth. This is because space is expanding, which lengthens both the wavelengths of light and the duration of events, making cosmic occurrences appear to happen more slowly. However, there are theories that suggest time itself could be affected in ways we don't fully understand. Accelerated expansion could lead to a universe where time behaves differently, on a cosmic scale, which could change the way we experience and measure time in fundamental ways. One theory is that expansion could cause the universe to freeze or heat death, in which case all the stars would burn out, galaxies would drift apart, and the universe would be a cold, dark place. In this future, without stars to mark the passage of time, the concept of time could become meaningless or even end. As the cosmos continues to expand, space and time may appear to vanish. This is because, as general relativity teaches us, time is relative and can flow at different rates depending on the gravitational field and the motion of objects. For instance, clocks tick more slowly near massive objects like black holes due to their strong gravitational pull. Known as gravitational time dilation, has been proven experimentally through methods such as comparing the timestamps of ground-based and aerial or space-based clocks. The question of whether this phenomenon could occur on a galactic scale, with space's expansion impacting the passage of time, is still unclear. Accelerated expansion, driven by dark energy, does impact our perception of time at great distances, but how this could impact the flow of time in the far future of the universe is an open question. The nature of time and its relationship to the universe's structure and the limits of expansion raise the intriguing question of what happens on the smallest scales. While we tend to think about the cosmos in terms of its large-scale expansion, what happens on the smaller scales is just as important. Does the expansion of the universe affect the quantum world, where particles like electrons, protons, and, at its core, photons exist? As the universe expands, the distance between galaxies and clusters of galaxies grows. However, the expansion of space doesn't appear to have much of an impact inside galaxies, and particularly within smaller structures like stars, planets, and atoms. The forces that bind these objects together, like gravity, electromagnetism, and a strong nuclear force, are fundamentally stronger than the effects of cosmic expansion at these smaller scales. At the quantum level, fundamental forces like the strong nuclear force that binds quarks inside protons and neutrons, and the electromagnetic force between electrons and protons keep atoms and planets in orbit even as the universe expands around them. These forces are far stronger than the weak effects of cosmic expansion, which means that even larger structures like rocks and humans are held together by these forces. Our everyday lives are unaffected by the expansion of the universe because quantum processes continue unabated despite this fact. The strong nuclear force, for example, is 100 times stronger than electromagnetism and millions of times stronger than gravity. It is this force that keeps protons and neutrons tightly bound within an atom's nucleus, preventing the expansion of the universe from having any discernible impact. While it may appear that the expansion of the universe has no bearing on the quantum realm, scientists are still exploring intriguing connections between cosmic expansion and quantum theory. One such connection is the fact that the forces that bind matter on small scales are simply too strong for the universe's gentle stretching to pull them apart. Neither your atoms nor the air molecules around you are expanding. Quantum theory teaches us that even in apparently empty space, there are instances when particles appear and disappear. These fluctuations happen on extremely tiny scales, much smaller than atoms. Some cosmologists think that these quantum fluctuations drove the expansion of the early universe, particularly during cosmic inflation, when a universe sped up from subatomic to cosmic scales in an instant. In the blink of an eye, during the inflationary period, quantum fluctuations propelled through space-time laid the groundwork for the galaxies and cosmic structures that we see around us today. In this way, the quantum world is the source of space's expansion, even though scientists are still trying to pin down exactly how the two relate. Another possible connection between quantum theory and the expansion of the universe is the idea of dark energy. If dark energy is indeed related to there may be a closer relationship between the expansion of the universe and the behavior of space on the smallest scales than is currently understood in the quantum realm. Many scientists have speculated about the long-term implications of the universe's expansion, with the heat-death theory being one of the most popular hypotheses. This theory proposes that if the expansion of the universe continues at its current rate, it will eventually reach a point where all energy is evenly distributed. The final state of equilibrium, where no further work can be done, is sometimes called the heat death. To understand this, let's take a look at the concept of entropy. Entropy is a measure of the disorder or randomness in a system in the universe. As time goes on, entropy increases, meaning systems become even more disordered. When a system reaches maximum entropy, there is no more energy available to create change or sustain processes. For example, the heat generated by stars is a type of. The concept of heat death arises from the fact that, as the universe expands, the energy it contains becomes less concentrated and hence less capable of powering objects like galaxies and stars. As a result, stars gradually deplete their fuel over billions and trillions of years, eventually collapsing into black holes, fading into icy dwarfs, or exploding into supernovae. As the cosmos expands at a rate greater than the speed of light, the Milky Way and its nearby galaxies may merge in the far future, but beyond that, other galaxies will fade from view. In this scenario, the cosmos becomes increasingly barren, with small pockets of matter encircled by huge stretches of nothingness. Eventually, the only source of energy left over is the weak radiation from the Big Bang. While black holes appear eternal, even the biggest ones will eventually evaporate, leaving behind only low energy, as predicted by physicist Stephen Hawking. This process causes black holes to gradually lose mass by emitting tiny amounts of radiation over extremely long time scales. In the end, the universe will experience occasional explosions from decaying black holes, but according to the heat death scenario, black holes themselves will evaporate. The universe will be a frigid, dark, an empty place once all the black holes have dissolved and the matter has broken down into its component parts. This state is sometimes called the Big Freeze. In this far future, when all matter has decayed into its most basic forms, there will be no stars, galaxies, or black holes. What will remain is a soup of low-energy particles scattered across a vast, endless void. This point marks the heat death of the universe, when the universe has reached its maximum entropy. It's important to note that the heat death of the universe is just one possible outcome based on current understanding of cosmic expansion, dark energy, and the laws of thermodynamics. In this state, all energy is evenly distributed without energy differences, and processes like star formation, chemical reactions, or even movement at the atomic level would come to a standstill. One of the main factors pushing the universe towards heat death is the role of dark energy. If dark energy continues to dominate the universe's behavior, it could prevent new structures from forming, sealing the fate of the universe as a cold, expanding void. This scenario may appear bleak, but there are still many unknowns in cosmology, and our knowledge of the universe's long-term future could change as new discoveries are made. It's worth noting that the universe is currently experiencing a relatively active phase, with stars forming galaxies, colliding, and life existing in pockets across the cosmos. The heat death scenario represents the very distant future, far beyond the lifespan of our solar system, Earth, or even the Milky Way galaxy. It's a violent end to what should be an incredibly long timeline for the heat death of the universe. A far more violent and abrupt end to the cosmos is imagined in the Big Rip hypothesis, where the expansion of the universe doesn't just continue at its current rate, but accelerates to the point where the fabric of space-time tears apart, taking everything within it. Unlike the gradual cooling and fading associated with the heat death scenario, the idea of the universe expanding endlessly is already strange enough. The Big Rip scenario begins with the Big Rip theory postulates that dark energy, which is currently exerting a relatively weak effect of slowly drawing galaxies apart, could grow stronger in the future. If this happens, the universe could expand at an ever-increasing rate, eventually becoming so intense that it surpasses the fundamental forces that hold matter together. This acceleration of the expansion of the universe is largely attributable to dark energy. In this scenario, the vastness of space would cause galaxy clusters, which are held together by gravity, to start drifting apart at speeds greater than the speed of light. This would isolate entire areas of the universe from one another. As the expansion of the universe picked up speed, galaxies themselves would be pulled apart. The forces of gravity that keep stars in their orbits around galaxy centers would be overpowered by the stretching of space, and the stars would scatter into the ever-expanding cosmos. Void, but the Big Rip doesn't end there. As the rate of expansion increases, even smaller structures like solar systems will be affected. Eventually, the force of expansion will surpass the gravity that keeps planets in orbit around their stars, and the planets will be torn apart, drifting off into the expanding emptiness of space. This acceleration will continue until it reaches truly terrifying scales, and dark energy will eventually overcome the forces that hold atoms together. As the universe continues to expand at an infinite rate, the electromagnetic force that holds electrons in atomic nuclei will eventually be unable to keep up with it. In this catastrophic future, atoms will be ripped apart, leaving behind only subatomic particles scattered across an expanding void. In the last moments of the Big Bang, the laws of physics that govern particle behavior and energy will no longer apply. The Big Bang could theoretically happen relatively quickly on a cosmic timescale if certain conditions were satisfied. One important idea is that dark energy's behavior might change over time. Currently, dark energy seems to have a relatively constant effect on the expansion of the universe. However, this catastrophic end could happen in a finite amount of time, leaving behind only isolated particles in a space that stretches infinitely fast in every direction. The nature of dark energy is still not completely understood, but according to some theories, it could grow stronger and more dominant as the universe evolves. If this path is followed, the Big Rip could happen because the expansion of the universe is accelerated to an unstoppable rate. On the other hand, if dark energy stays constant, as many models predict, then the Big Rip won't happen and the universe will go toward heat death more gradually. A more exact measurement of dark energy and its properties is necessary to determine whether the Big Rip will occur, but observations of faraway galaxies and supernovae have given strong evidence that the universe is expanding and that this expansion is accelerating. Astronomers and physicists have been studying these topics in order to gain a better understanding of the Big Rip and its potential consequences. The Big Rip could happen as early as 22 billion years from now, depending on the strength of dark energy and how rapidly it accelerates the expansion. This may seem like a very short time compared to the long-term future of a universe heading toward heat death, which could take unimaginably long, trillions of years or more. Are we currently experiencing an expanding universe simulation? The theory of the universe as a simulation has recently gained a lot of attention, but it has deep philosophical roots in discussions about perception and reality. Some scientists and philosophers are seriously considering the possibility that we are living in a simulation due to the rapid advancements in computing and technology. Philosopher Nick Bostrom is a prominent proponent of this idea. He suggested in 2001 that advanced civilizations may have been involved in. From this vantage point, the expansion of the universe could be one of many programmed features in the simulation, similar to how modern video games or virtual reality experiences portray space and time for players. The simulation could follow the same rules as the expansion we observe with galaxies moving away from one another. In the distant future, it is possible to create simulations of entire universes, and the inhabitants, like us, could be completely oblivious to the artificial nature of their reality. What's intriguing about this theory is that, similar to how a video game's world grows or changes depending on the player's movement or actions, our universe could be expanding in a way that aligns with the rules of the simulation. This expansion, which is accelerated due to dark energy, could be a part of the simulation's evolution. Perhaps the stretching of space itself is just a feature programmed into the simulation to give it an authentic feel. It's possible that the universe is expanding not because of fundamental physics, but because of the computational rules that govern the simulation. This could be because the creators of the simulation decided to continuously expand it, rather than because of any natural process governing the expansion. This could explain why our expanding universe could be a result of the simulation rather than a natural process governed by fundamental physics. The limits of what can be seen are expanding at an ever-increasing rate, creating the illusion of a universe that seems to be expanding forever. This expansion, in turn, raises questions about the simulation's limitations. After all, if the universe is really expanding at an ever-increasing rate, then the simulation must be constantly creating new space to accommodate it. This would be similar to how computer simulations often generate environments dynamically as the user explores new areas. If we are indeed living in a simulation, then certain cosmic phenomena may actually be glitches in the simulation itself, rather than being the result of physical laws pushing the universe to expand. This is an intriguing aspect of the simulation theory to consider, especially in light of our growing knowledge of the cosmos, which demands ever-increasing amounts of space for the simulation to accommodate. In a simulated reality, there may be a limit to what we are allowed to see or experience. For example, the mysterious behavior of dark energy, which appears to be pulling the universe apart at an accelerating rate, could be an unintended consequence of the simulation's parameters. This would explain why dark energy acts in such a mysterious and baffling way, and it could also shed light on why we have struggled to fully understand it. Cosmology's Eichel horizon, the point beyond which light hasn't had enough time to reach us since the universe began, may be an intentional boundary programmed into the system to prevent us from ever being able to fully observe or interact with some regions of the cosmos. The expansion of the universe, which is pushing distant galaxies beyond this horizon, may also be a mechanism for keeping this boundary within the simulation. It's possible that the rules of the simulation govern both the flow of time and the expansion of the universe. This would explain why the expansion of the universe seems to be speeding up as the simulation goes on. The creators could be adjusting the rate of expansion, either because it's a natural consequence of the simulation's parameters, or because it's a deliberate decision. While cosmologists and physicists have long considered the expansion of the universe to be a natural process, recent speculation regarding the role of exotic forms of matter and energy in this process has led scientists to consider the possibility that we may be living in a simulation. The simulation hypothesis offers an intriguing alternative perspective on cosmic expansion and the universe at large. Exotic, hypothetical forms of matter and energy that don't behave like anything we know could hold answers to some of the most profound mysteries surrounding the expansion of the universe. One of the biggest puzzles in cosmology is the nature of dark energy, which is basically invisible and undetectable, unlike ordinary matter and energy. It doesn't appear to interact with anything in the way we expect, except via its effects on the large-scale structure of the universe. Dark energy appears to be propelling the universe's continued expansion at an ever-increasing rate. However, its precise nature remains a mystery, leading some to speculate that it may be an exotic force unique to our universe, exhibiting behavior unlike anything we've ever encountered. It's conceivable that changes in its properties could cause fluctuations in the rate of expansion, which in turn could affect the rate of expansion throughout space. This could explain why we see the expansion of the universe slowing down or speeding up over time, as if something in space is changing in ways we don't yet fully comprehend. Another theory is that there is exotic matter, which is different from the ordinary matter that forms galaxies, and some theories propose that exotic matter could have negative mass, meaning it repels rather than attracts other forms of matter. If this form of matter existed, it could counteract gravity's effects, which normally slow down expansion on smaller scales. Some models also suggest that certain regions of the universe may contain higher concentrations of exotic matter, or that it could exhibit unusual properties that cause it to behave differently in the context of cosmic expansion. It's possible that some areas could expand faster than others, depending on the amount of exotic matter and energy present. This could cause some areas to appear to be expanding at a uniform rate on large scales, but in reality, different regions could be experiencing different rates of expansion. Some theories even suggest that exotic matter and energy could actively affect the shape of spacetime in general relativity, affecting the distribution of mass and energy. When ordinary matter is present, it bends space in a way that allows stars, planets, and galaxies to form. However, exotic matter, due to its peculiar properties, has the potential to bend space in a completely different way. Some scientists have speculated that exotic matter could cause space to expand or contract in unexpected regions, or even form bubbles of spacetime that act differently than the rest of the universe, might contract or expand more rapidly, causing strange effects like the birth of parallel universes. If these theories hold, the expansion of the cosmos could be much more complicated than a uniform process, with exotic matter and energy shaping it in ways we can't see directly. If this exotic energy does exist, it could be used to control or even reverse the expansion of the universe. For the time being, this is all very much in the realm of speculation. In the realm of speculation, there are scientists who have pondered the possibility of manipulating space's expansion. If we could somehow communicate with dark energy or other mysterious forces, they say we could develop technology to expand or contract regions of space on demand. This, in turn, could open up new possibilities for future civilizations. For example, if we could find a way to influence the rate of expansion locally, it could lead to new ways of traveling through space or even the formation of isolated pockets of. As far as the Big Bang and Big Bang are concerned, the fate of the universe depends on the expansion of space and what it implies for matter, energy, and the forces that govern the cosmos. Various theories have attempted to explain this phenomenon, but ultimately, the fate of the universe depends on the expansion of space itself, whether it continues to expand indefinitely, stops expanding, or even reverses its course. One of the previously mentioned scenarios is the Big Crunch, which proposes that the universe's expansion could one day come to a halt and start contracting. As time went on, galaxies, stars, and planets would draw closer together, eventually collapsing into a single point, creating a situation reminiscent of the Big Bang, but with the expansion happening in the opposite direction. The Big Crunch is a theory that has not been proven yet, because observations show that the universe is expanding at an accelerating rate. However, it could happen if dark energy were to undergo a change in the future. Another theory is related to quantum mechanics and the vacuum decay. According to this theory, the universe could be in a temporary unstable state called a false vacuum, and it could transition to a more stable version of space at some point. This change could happen at any moment without prior notice due to a quantum fluctuation. If it did, it would produce a true vacuum bubble that expands at the speed of light, annihilating everything in its path. The universe, as we know, it would vanish as it is supplanted by this vacuum. Other theories speculate about the multiverse, with some suggesting that black holes could serve as doorways to alternate realities, and as our own universe fades into oblivion, new ones could spring up. This would imply that, although our own universe may have an end, the multiverse goes on in an endless loop of creation and destruction. The question that naturally follows is, would life be able to endure a universe that is cold and stretched out? The most probable outcome, according to this theory, is a cold stretch state, sometimes called the Big Freeze or heat death. In this scenario, stars burn out, galaxies drift apart, and the cosmos gets dark and frigid. Although the idea of life surviving in such a universe may appear implausible at first, the adaptability and persistence of life, as we know, it makes it worthwhile to investigate how life could endure such harsh conditions. In our current cosmos, stars provide energy, sunlight powers ecosystems, and the heat from stars is essential for keeping planets like Earth habitable. However, in a universe where stars have burned out and temperatures have plummeted near zero, this wouldn't be the case. If life were to persist, we would need to find ways to power it. One theory suggests that black holes, which remain in the universe even after stars die, could be a source of energy. Some believe that matter colliding with a black hole releases vast amounts of energy, which could be harnessed by civilizations to endure the vast, dark universe. Another possibility is that life could, in order to adapt to environments that appear uninhabitable to most forms of life, such as deep-sea hydrothermal vents, frigid Arctic waters, or extremely radioactive environments. There are examples of extremophiles organisms that thrive on Earth. If these creatures were able to survive in such extreme conditions, then maybe with enough time, life could evolve to survive in the cold, expanded universe. It's possible that life in the far future will be completely different from what we know it to be today, with biochemical processes that use significantly less energy than what we see today. Technology could also help life extend its lifespan. If advanced civilizations manage to build artificial habitats or environments with controlled conditions, they could construct massive structures to collect and store energy from the universe's last remaining sources. Civilizations may also discover ways to reduce the amount of energy needed to survive by slowing down their metabolic processes. Time could become a key resource as they endeavor to extend their existence using the limited energy available. Another possibility is that intelligent life may discover ways to manipulate the fabric of a universe. This could involve tapping into exotic physics, like dark energy or quantum fields, too. The vast potential for innovation and adaptation that could arise from advanced civilizations confronted with the challenge of surviving in a dying universe is reflected in these speculative ideas about creating new sources of energy. However, even with these advancements, there are limits to how long life could stay in an ever-expanding, cooling universe. As the universe stretches further, the distance between galaxies grows larger, isolating any remaining civilizations from communication and travel between galaxies. As the universe continues to expand at a rate greater than the speed of light, all processes slow down as the temperature approaches absolute zero. This impacts the fundamental laws of physics, which in turn slows down chemical reactions and biological processes. Eventually, all life becomes impossible as civilizations become isolated in their own local regions of space, cut off from any other possible civilizations. Imagine a world where all forms of life, no matter how efficient, are faced with the challenge of finding enough energy to survive. What if, in the distant future, life doesn't depend on carbon or other familiar elements? What if consciousness evolves into a form that is purely informational, where energy is needed to support basic functions like reproduction or thinking? Some radical theories propose this alternative. Could life exist in a digital or quantum state even after the physical universe becomes too cold to sustain biological life? These forms of life could theoretically exist independently of physical matter and could theoretically endure indefinitely after the universe's energy is exhausted. Another theory is that life could escape to other universes where there might be different physical laws or different conditions. The potential for advanced civilizations to find means of transport between universes, leaving this one behind as it cools and expands, presents an opportunity for life to thrive in a more favorable environment as our own universe winds down its expansion. This, in turn, raises important questions about the future of cosmic communication and, more importantly, the impact on galactic civilization's capacity to While galaxies now are relatively close together in the universe, as the universe expands, their distance from each other will grow until communication is practically impossible. This means that any kind of communication, such as radio signals, electromagnetic waves, or even hypothetically advanced communication technologies, will become more difficult, if not impossible, to establish. Eventually, even visible galaxies will disappear from view. There is no evidence that communication between distant civilizations was feasible in the early days of cosmic evolution. But as time progresses and cosmic expansion accelerates, even the possibility of future communication becomes more plausible. For civilizations existing in different galaxies, the horizon becoming visually and communicatively unreachable could have profound consequences. Galaxies will eventually fade away, ushering in a period of cosmic isolation whereby galaxies, or more precisely, clusters of galaxies, will become their own isolated cosmic island, cut off from the rest of the cosmos by impassable distances. The consequences of this isolation will go far beyond the mere impossibility of communication. As galaxies pass beyond the visible horizon, they will essentially vanish from view, and distant civilizations will have to settle for seeing only those galaxies in their own local cluster. As the cosmos descends into darkness, this isolation could have repercussions for the sharing of information and resources. If advanced societies had figured out ways to trade across galaxies or share scientific discoveries, these activities would become more and more impractical, and civilizations would have to depend solely on the resources and knowledge within their own galaxy. The concept of a cosmically linked universe, which is still theoretical at this point, would fade into oblivion. Therefore, galaxies would be separated by a barrier that no amount of information or technology could ever break through. Not even the most cutting-edge methods of communication, which surpass our current understanding, could escape the constraints of space's endless expansion and the speed of light. No signal, no matter how strong, could ever traverse the vast distances between galaxies quickly enough to support the civilizations that call them home. On a smaller scale, communication and exploration within our galaxy would still be feasible. The problem with cosmic expansion arises when we try to connect galaxies that aren't gravitationally bound to each other. On a larger scale, within individual galaxies or clusters of galaxies, gravitational forces are strong enough to resist expansion, so communication and interaction can continue. Black holes in an expanding universe pose a threat of isolation. How will civilizations adapt to this reality? Will they discover ways to leave a record of their existence before expansion makes them unreachable? Or will they turn inward, relying on their own galactic neighborhood for survival and growth? Whatever the case may be, it is intriguing to explore the role and fate of black holes, particularly in light of their potential influence on the long-term fate of cosmic expansion. Black holes in an expanding universe are known to grow in size by absorbing matter and merging with other black holes. However, as the universe expands and galaxies drift apart, the amount of matter available for black holes to consume gradually diminishes, leading to an increasingly empty universe. This is a crucial aspect of black holes for any advanced civilizations that may exist in the distant future. As the universe expands and cools, the density of matter decreases, and black holes become more isolated. They will have less material to draw in, slowing down their growth. Eventually, they may stop growing altogether, existing as the last remnants of a universe filled with stars and galaxies. Despite this decline in available matter, black holes remain remarkably persistent in the cosmos. Stars burn out and galaxies fade away, but black holes can endure for extremely long periods of time. Despite the fact that the universe is expanding and cooling the evaporation process, the most massive black holes, those located at the galactic centers, may outlast nearly everything else in existence. These black holes will remain long after stars have used up their fuel and galaxies have ceased to form. Over extremely long periods of time, black holes slowly emit Hawking radiation, which causes them to lose mass and eventually evaporate. It's possible that black holes will ultimately vanish, but until then, they could play an important role for advanced civilizations that face an increasingly hostile universe due to cosmic expansion and dwindling energy resources. This might happen in a very distant future, when the universe reaches its heat death, when entropy increases to the point where no usable energy is left. One way to tap into black hole energy is through the Penrose process, which involves guiding objects into the area surrounding a spinning black hole to harness its rotational energy. This could allow civilizations to keep producing power even when stars grow fainter and other energy sources become unavailable. Another way is to utilize the gas and dust that forms around black holes, which is known as the accretion disks. Even though the universe is constantly expanding, some black holes will retain accretion disks for a long time because they keep drawing material from their surroundings. This could provide advanced civilizations with a lifeline in an otherwise dimming cosmos. Black holes could also offer a way for civilizations to preserve knowledge or even survive for longer periods of time. Some have even proposed that civilizations could build structures to contain this energy. In the vicinity of black holes, the tremendous gravitational pull slows down the passage of time compared to the rest of space. With this time dilation, civilizations may be able to live on for a longer period of time, effectively extending the universe's unending expansion. In this scenario, black holes could be seen as the final strongholds of complexity in an otherwise chaotic cosmos. Black holes, with their powerful gravitational fields and unique characteristics, provide one of the few remaining sources of order and energy in a universe heading toward increased entropy. Whether they're used as energy sources by the last civilizations or simply as cosmic artifacts, their presence will shape the final chapter of the universe's history, which is ever simplifying as the universe expands and matter becomes more diffuse. The current generation of telescopes has provided us with incredible insights into the nature of cosmic expansion, but future instruments promise to take these discoveries even further. Scientists and engineers are working on state-of-the-art telescopes and spacecraft to ensure that humanity has the most advanced technology available to observe the cosmos and shed light on our ignorance. The James Webb Space Telescope, also known as the JWST, is one of several observatories that will enable us to delve further into the cosmos, uncovering new information about its history, expansion, and potential future uses. It was built to replace the Hubble Space Telescope, which had previously provided remarkable images and data, particularly regarding the redshift of galaxies and the early universe. The JWST, on the other hand, is able to observe infrared light, allowing it to peer even farther into the past, since, as the universe expands, light from faraway galaxies can be stretched into. JWST is designed to capture light at longer infrared wavelengths, which helps us understand galaxies that formed shortly after the Big Bang. By studying these early galaxies, we can learn about the expansion of the universe and how it has changed over time. The European Space Agency, SAA, is also involved in this exploration of cosmic expansion through missions like the Euclid Space Telescope, which is designed to study dark matter. Dark energy, which is propelling the universe's rapid expansion, is still largely a mystery. The Ultra Deep Field, ULF, aims to fill this knowledge gap by charting the distribution of galaxies and galaxy clusters across space and time. With this massive map in hand, scientists can better understand the role of dark energy in the expansion of the universe. The Square Kilometer Array is an ambitious international project aiming to construct the biggest radio telescope in the world. Unlike traditional optical telescopes, which use visible light to study the universe, the SKA will use radio waves, which are less affected by cosmic dust. This will allow the SKA to peer through obstacles that block other types of light, thanks to its extensive network of antennas spread across. Scientists will gain a better understanding of the effects of cosmic expansion on the distribution of matter and energy when they use the SKA to gather extremely detailed data on faraway galaxies, cosmic background radiation, and the universe's large-scale structure. However, studying cosmic expansion isn't limited to observing galaxies. The upcoming generation of gravitational wave detectors also promises to reveal new information about the expanding universe, as gravitational waves are ripples. Gravitational waves are a novel method of exploring the cosmos, formed by violent events like black hole collisions. These waves propagate through space and time, carrying information about the structure of space-time. In the future, detectors like the Laser Interferometer Space Antenna, or LISA, will be able to detect these waves more sensitively than current instruments. By analyzing these waves, scientists can learn more about the expansion of space on both large and small scales. Their invulnerability to light and matter makes them an invaluable resource for astronomers studying cosmic evolution. New methods of data analysis and computer simulations are assisting astronomers in making sense of the massive amounts of data generated by modern telescopes. Artificial intelligence, AI, algorithms are being created to sort through this data, find patterns, and predict how cosmic. In order to study the early stages of a universe's expansion, it will be crucial to conduct missions to study the cosmic microwave background, CMB. Telescopes like the Planck satellite have already produced detailed maps of the CMB, revealing the tiny fluctuations that cause the formation of galaxies and galaxy clusters. The ability to track the movement and evolution of galaxies over billions of years makes these tools ideal for studying cosmic expansion. In the future, missions will improve these measurements even more, which will shed light on how cosmic inflation, the quick expansion of space-time immediately following the Big Bang, set the stage for the universe's ongoing expansion. Meanwhile, ground-based telescopes like the Virgin Observatory will conduct extensive surveys of the sky by constantly scanning vast portions of space-time. The Rubin Observatory, for example, will be able to monitor the movement of millions of galaxies, offering detailed information on the vast structure of the cosmos will be uncovered by this observatory, which will aid in our comprehension of dark energy by tracking the motion and evolution of galaxies and supernovae. By keeping a close eye on the sky on a regular basis, scientists will also be able to spot unforeseen phenomena, providing an opportunity to study events connected to cosmic expansion as they unfold. When it comes to the mysteries of the cosmos, will our understanding ever be sufficient to fully comprehend them? While science has come a long way in explaining the expansion of the universe and how we can observe it, many questions about the nature of reality, time, and space continue to be unanswered. For instance, we know that distant galaxies are moving away from us, and that this acceleration is caused by dark energy. However, the exact nature of dark energy and why it occurs, as well as what lies beyond the expansion and whether or not it will ever cease, are still mysteries. It is one of the biggest mysteries in modern science. We can see its effects, but we don't know what it is. Is it a force, a field, or just a property of space? And why did it start controlling the expansion of the universe at a certain point? These questions test our basic understanding of the universe. The cosmological horizon limits our knowledge, so we can't explore beyond it. It's like being stuck in a knowledge bubble with no way out. The complexity of cosmic expansion may outstrip human comprehension. Theoretical physicists utilize exceedingly intricate equations to depict the expansion of space, the formation and movement of galaxies, and the impact of dark energy on these processes. However, there's a distinction between just describing something and actually experiencing it. As a result of our limited understanding of cosmic expansion, human perception and reasoning are influenced by our experiences on Earth. Where time moves forward in a linear fashion, space is relatively stable, and natural forces behave in predictable ways. However, we still have a long way to go before we can fully comprehend the deeper why behind these behaviors. It is believed that time may act differently at the most massive scales, and the idea of infinite space goes against our natural inclinations. Our brains aren't designed to handle concepts like infinity or four-dimensional space, let alone the prospect that space could be infinite. Nevertheless, these abstract notions continue to expand our understanding of the universe, and some contend that this is due more to a lack of knowledge than to a lack of adequate technology. Although we can observe the effects of cosmic expansion, the true nature of the universe may be so complex that it surpasses our ability to fully understand it. Nevertheless, there is always a drive in science to push beyond these limits. The expansion of the universe went from being an unimaginable idea to something that is now becoming increasingly apparent. Whether these mysteries will always elude human comprehension or if we are just waiting for the next big discovery is an unanswered question. What are your thoughts on the matter? Please share your thoughts in the comments section. If you liked the video, please consider giving it a thumbs up and subscribing. Thank you for watching.